So lesson 14, implicit differentiation. This is section 3.5. So the idea is we know how to find the derivative of a function. So if we're given y equal 3x squared minus 5, then dy dx is 6x. So this is y is an explicit function of x. In this example, y is exactly this function of x, and we differentiate it. Now, suppose we have something more subtle. Suppose we're given a curve. The first example in the book is y cubed plus y squared minus 5y minus x squared equals minus 4. So the curve means find all the points in the plane that satisfy this equation. And there's a nice picture of what the curve looks like in the text. It looks something like that. So it's not just a function of y, is not just a function of x. We have this curve. And on this curve, we can check that the point xy equal to 1, 1 lies on the curve. How do we know that? Because if you plug in x equal 1 and y equal 1, you get 1 cubed plus 1 squared minus 5 times 1 minus 1 squared. What is that? That's 2 minus 5 is minus 3. That is minus 4. So this point, 1, 1, lies on the curve. The point xy equal to 1 minus 3 also lies on the curve. Why do we know that? Because if you plug in x equal 1 and y equals minus 3, you get minus 3 cubed plus minus 3 squared minus 5 times minus 3 minus 1 squared. That's minus 27 plus 9 plus 15 minus 1. So this is minus 27 minus 28 plus 24. That's minus 4. So this point, 1 minus 3, also lies on the curve. Right? Now, in any region, in any small interval around either one of these points, you actually have y as a function of x. And up here, y is a different function of x. So around either of these points on the curve, there's some function y of x defined implicitly by this equation. So let me just say there are functions defined implicitly by the curve. I can't write them down explicitly, but we know they're there. And in fact, it's often possible, even though we cannot write the function explicitly, to compute its derivative. And so there is a function y defined implicitly. And we want to find what is dy dx. Now note, if you had like y cubed, what is the derivative of y cubed with respect to x? By the chain rule, this is the derivative of y cubed with respect to y times dy dx. And the derivative of y cubed with respect to y is 3y squared dy dx. So if y is a function of x, if you're differentiating a power of y, like y cubed, you get 3y squared dy dx. And this simple fact we use all the time. So if we start with the curve, y cubed plus y squared minus 5y minus x squared equals minus 4, and we want to find, so we have this curve, and we want to find dy dx. So the derivative with respect to x of the left-hand side is the derivative with respect to x of the right-hand side. Of course, this is just a constant. We know that's 0. And what is this? This is the derivative. We can differentiate term by term. The derivative of y cubed with respect to x plus the derivative of y squared with respect to x minus the derivative of 5y with respect to x minus the derivative of x squared with respect to x. And what's the derivative of y cubed with respect to x? By the chain rule, that's 3y squared dy dx. The derivative of y squared with respect to x is 2y dy dx. This is just minus 5 dy dx. And the derivative of x squared with respect to x is 2x. So all that's equal to 0. Now, you can factor out dy dx. You get dy dx times 3y squared plus 2y minus 5 minus 2x equals 0 or equals 2x. So dividing by this, we get dy dx equals 2x over 3y squared plus 2y minus 5. So this is what is called implicit differentiation. You have a curve defined implicitly, you have a function defined implicitly by an equation, and at some point on the curve, this is the derivative. So for example, at the point xy equal to 1, 1, which we saw lies on the curve, dy dx would be 2 times 1 over 3 plus 2 minus 5. This looks like 2 over 0, so this is undefined. So in fact, at this point, there is no derivative. But at the other point we saw lay on the curve, 1, negative 3, dy dx is equal to 2 times negative 3 over, 2 times x, 2 times 1 over 3 times minus 3 squared plus 2 times minus 3 minus 5. That's 2 over, this is 3 times 9 is 27, minus 6 minus 5, 27 minus 11 is 16, is an eighth. So when we saw that the equation of this curve looked like this was the point 1, 1. This was the point 1 minus 3. Here there's no derivative, but at this point the derivative is 1/8. So there actually is a tangent line to the curve at this point with slope 1/8. So this is a new technique. This we have not seen before. And if you're lucky in your computer lab, you will be able to take a curve defined implicitly by an equation and get Maple or whatever program you're using to graph it and draw the tangent line on it so you can see how pretty this all looks. Okay. Let's do more and more examples. So suppose we take the ellipse. X squared plus 4y squared equals 4. In any case, this is a curve and the graph really is an ellipse. Find the slope of the tangent line at the point square root of 2 minus 1 over the square root of 2. So before I do the algebra, the calculus, let's just draw a picture so we can see what's going on. X squared plus 4y squared equals 4. If I divide by 4, I get x squared over 4 plus y squared equals 1, or x squared over 4 is x over 2 squared plus y squared equals 1. So in pre-calculus, you're supposed to learn the equation of an ellipse. This is an ellipse where the major axis is from -2 to +2, and the minor axis is from -1 to 1. The graph of the ellipse looks like this. And if you let x equal root 2 and y equal minus root 2, you get x squared, root 2 squared, plus 4 times minus 1 over root 2 squared. Let's see, what is that? That's 2 plus 4 over 2, which is 2 plus 2, which is 4. So this point does lie on the ellipse. It's right over there. And we want to find the slope of the tangent line. So let's use implicit differentiation. If you have x squared plus 4y squared equals 4, the derivative with respect of the left-hand side is the derivative with respect of the right-hand side, which is 0. Derivative of x squared is 2x. The derivative of 4y squared is 4 times 2y dy dx equals 0. So this says that 8y dy dx is minus 2x. So dy dx is minus x over 4y. And at this point, root 2 minus 1 over root 2 dy dx is minus x over 4 times minus 1 over root 2. So this is the minus signs cancel. 4 over root 2 is 2 root 2. So we get a half. So the tangent line has slope a half. Okay, well, let's keep doing some examples. Suppose we have the curve 3x squared plus y squared squared equals 100 xy. Notice at the point xy equal to 3, 1, 3 times x squared plus y squared squared is 3 times 9 plus 1 squared. That's 10 squared is 100 times 3, this is 300. And 100 xy is 100 times 3 times 1, which is also 300. So this point lies on the curve. I mean, in fact, this curve, the picture in the book says, this is just a figure 8. And here's the point 3, 1. What's the slope of the tangent line at this point? We have to differentiate. So the derivative with respect to x of 3x squared plus y squared squared is what? 3 times the derivative with respect to x of x squared plus y squared squared. So that's 3 times 2 times x squared plus y squared times the derivative of x squared plus y squared. Let's see, 3 times 2 is 6, x squared plus y squared. The derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x is 2y dy dx. So we get 12 x squared plus y squared times x plus y dy dx. That's the derivative of the left-hand side of that equation. And what's the derivative of the right-hand side? The derivative of 100 xy is 100 times the derivative of xy with respect to x. By the product rule, that's the derivative of x with respect to x, which is 1 times y plus x times dy dx. Right? So, and these two functions are equal, their derivatives are equal, so we set this equal to this. So we have 12 x squared plus y squared, x plus y dy dx equals 100 y plus 100x dy dx. And we have to solve for dy dx. Let's see, this is equal to 12x times x squared plus y squared plus 12y x squared plus y squared dy dx equal to 100y plus 100x dy dx. So if I solve for dy dx, bring this over here and this over there, I get dy dx times 12y x squared plus y squared minus 100x equals 100y minus 12x times x squared plus y squared. So if I take this and divide by it,
Professor, can you move the paper up?
yep.
Thank you.
So 12y times x squared plus y squared minus 100x. And you can divide by 4 if you like. And you get whatever turns out to be the answer. I mean, that's what the answer is. This is example 5 in the text. You can simplify this slightly more, but not really. And then if you want to know the slope of the tangent to this curve at the point 3, 1, you plug in x equal 3, y equal 1, and you get out the answer. Right? Okay. Again, this is supposed to be hard only because it's new. And after you've done 10 or 20 problems using implicit differentiation and become familiar with the technique, it'll be easy. I noticed that someone had put a question on chat about 45 minutes ago, which I just saw. So really, if you have a question about how something that we're doing, just unmute yourself for a minute and ask, because that way I'll definitely hear you. But if you put it on chat, there's a good chance I won't see it until it's way too late. Let's look at another example in the book. It's example 6. So suppose we have the curve sine of y equals x. If it were x equals sine y, sorry, if it were y equals sine x, the graph would look like that. But for x equals sine y, looks like that. Suppose we want to find dy dx. So the derivative with respect to x of the sine of y is the derivative with respect to y of sine of y times dy sine of y with respect to y times dy dx. That's cosine y dy dx, and that's equal to x, the derivative of x, which is 1. So for this function, for this curve, sine y equals x, we get dy dx is equal to 1 over the cosine of y. Now, we can actually observe the following. We know that sine squared y plus cosine squared y equals 1. So cosine y is the square root of 1 minus sine squared y. And sine y is x. So this is the square root of 1 minus x squared. So for the curve defined implicitly by sine y equals x, dy dx is this. But of course, notice the sine of y is x. That means that y is the inverse sine or the arc sine of x. So what we just proved is the following. The derivative with respect to x of the arc sine of x is 1 over the square root of 1 minus x squared. So that's actually kind of amazing. Using implicit differentiation, we just found the derivative of one more fundamental function in mathematics, the arc sine. Okay. The derivative of the arc sine is 1 over the square root of 1 minus x squared. Okay. Good. Let's do 3 more examples. Again, I'm taking these from the book, so it makes it easy to study at home. This was example 6, which means the next must be example 7. So in example 7, we have a circle, x squared plus y squared equals 25, right? You know that's the equation of a circle of radius 5. And we want to find, using implicit differentiation, the second derivative of y with respect to x squared. The way you find the second derivative is first find the first derivative. So if you differentiate with respect to x, x squared plus y squared, the derivative of x squared is 2x. The derivative of y squared is 2y dy dx. And that equals the derivative of the constant function 25, which is 0. So you get 2y dy dx is minus 2x, which means dy dx is minus 2x over 2y, or minus x over y. So that's the first derivative. The second derivative is the derivative of the first derivative, which is minus x over y. We use the product rule. It's the denominator squared. The derivative, I'll put a minus sign in front. So it's the derivative of x over y. The derivative of x, which is 1 times y, minus the numerator x times dy dx. Well, we know dy dx is minus x over y. So this is minus y minus x times minus x over y times y squared. This is minus y minus times minus is plus x squared over y squared. So you get minus, if you put it over a common denominator, x squared plus y squared over y cubed. X squared plus y squared is 25. So you get minus 25 over y cubed. So let me go through this again, because again, this is a new technique to learn. We're given the circle of radius 5 with center at the origin. The curve is x squared plus y squared equals 25. And we want to use implicit differentiation to find the second derivative of y with respect to x. So the first thing you do is find the first derivative. If you differentiate both sides with respect to x, on the left you get 2x plus 2y dx, and on the right you get 0. So you solve for dy dx. The first derivative is minus x over y. The second derivative is the derivative of the first derivative. That means the derivative of minus x over y. So that's minus the derivative of x over y. By the quotient rule, you get a y squared in the denominator, the derivative of x, which is 1 times y minus x times the derivative of y. But derivative of y we found is minus x over y. So you plug this in here, you get y plus x squared over y. Multiply top and bottom by y. You get x squared plus y squared over y cubed. X squared plus y squared is 25. So that's the answer. Okay. This is example 8. So find the tangent line to the graph given by the following curve. We have x squared times x squared plus y squared equals y squared. And if you look at the point xy equal root 2 over 2, root 2 over 2, that means when you plug into the equation, what is x squared and y squared? So x squared and y squared are both equal to 2 over 4, or a half. So when you plug into this equation, what you get is a half times a half plus a half equals a half, which is true. So this point lies on the curve. And we want to find the tangent line to the curve at this point. So we have to find dy dx. So if we differentiate the left-hand side, by the product rule, that's the derivative of x squared times x squared plus y squared plus x squared times the derivative of x squared plus y squared. The derivative of x squared with respect to x is 2x. And the derivative of x squared plus y squared is 2x plus 2y dy dx. So what we get is 2x cubed plus 2xy squared plus another 2x cubed makes that 4x cubed plus 2 x squared y dy dx. And this is equal to the derivative of y squared with respect to x, which is 2y dy dx. So this equals this. So this is equal to 2y dy dx. So another way of writing this is that, bring this over to this side, 2y minus 2x squared y dy dx equals 4x cubed plus 2x y squared. So dy dx is equal to, let's see, what is this? I can factor out a 2x from this. 2x times 2x squared plus y squared over this. I can factor a 2y out of this times 1 minus x squared. These twos cancel. So the derivative is x times 2x squared plus y squared over y times 1 minus x squared. So what is this equal to at the point xy equal to root 2 over 2 root 2 over 2? You get dy dx is equal to x over y, x equals y, so they cancel. 2x squared, x squared is a half. This is 2 times a half plus a half over 1 minus x squared, which is a half. So this is 1 plus a half, 3 halves over a half. You get 3. So the derivative at this point is equal to 3. So the tangent line is y equal to the slope 3 times x minus root 2 over 2 plus root 2 over 2. So this is 3x minus root 2. Again, there's a lot of algebra here, but you know, algebra is a prerequisite to calculus, so you got to be able to do it. Again, this is example 8 in the text, so this is all clearly done and legible with a nice picture of the graph in the book. The very last topic in this lesson is another useful technique called implicit differentiation. So this is, sorry, logarithmic differentiation. So suppose we have a slightly complicated looking function like x minus 2 squared over square root of x squared plus 1. This is defined everywhere, and the only time it's 0 is when x is equal to 2, and I only want to consider the points where x is not 0, where y is not 0, so x is different from 2. And we could find the derivative by using the rules of calculus we already know. But a function like this you can simplify by taking its logarithm. So if you take the log of y, that's the log of x minus 2 squared over the square root of x squared plus 1. By properties of the logarithm, this is the log of x minus 2 squared minus the log of the square root of x squared plus 1. The log of something to a power, you can take the power outside. This is the log of x minus 2. And the square root is the power 1/2. So this is minus 1/2, the log of x squared plus 1. And now, if you differentiate with respect to x, the derivative with respect to x of the log of y, this is the derivative of the log of y with respect to y, dy dx. The derivative of the logarithm of y with respect to y is 1 over y, dy dx. And that's equal to the derivative of what's on the right-hand side, 2 times the log of x minus 2 minus 1/2 times the log of x squared plus 1. But we know how to differentiate a logarithm. This is 2 over x minus 2 minus 1/2, 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. So this is 2 over x minus 2 minus x over x squared plus 1. And that's equal to 1 over y dy dx. So this means that dy dx is just my function y that I started with times this. And I can simplify this if I like, because y is equal to x minus 2 squared over the square root of x squared plus 1 times 2 over x minus 2 minus x over x squared plus 1. So what I get is 2 times x minus 2 over the square root of x squared plus 1 minus x times x minus 2 squared over x squared plus 1 to the 3/2. And I can simplify it a little bit more if I like. But the whole point of this method called logarithmic differentiation is when you have a function which looks like a product and quotient of powers of simple expressions. If you take the natural log, you get something which is much easier to differentiate. And you can get an answer quickly. That's all. It's just a technique to speed up your work sometimes. Okay, any questions about any of this? So this is section 3.5, lesson 14 in the text on implicit differentiation. And it's interesting to observe that since there are 28 classes in a semester and we've just finished class 14, we are exactly halfway through the term. It's kind of interesting. Halfway home. All right, well.
Professor, do you think next semester is gonna be online as well?
Oh, I don't know